Hello and welcome to the Hexagon Summer webinar series in support of Formula SAE and similar vehicle competitions on how to use Hexagon simulation software to get an edge with these competitions and have a richer experience doing these activities. We're going to be talking about Romax today, and that's really exciting to me because when I was a professor, I taught mechanical design a lot, like design of gears and bearings in power transmissions, and that can be a very tedious process. It can be really tough. There are a lot of different things to look at, and you have to be able to think about things at different levels of detail as you go through the design process. And when I joined Hexagon, I was so excited to see what Romax is capable of. So to show you about Romax and show you how you can apply it to Formula SAE, Formula Student competitions like that, Ginny Roberts will be presenting. Jenny joined Hexagon's graduate scheme in 2023, where she gained hands-on experience across the various teams at Hexagon. So she didn't just deal with engineering simulation software, she also dealt with CAM software and was able to design and manufacture a bracket mount, and then she inspected it with a Hexagon coordinate measuring machine. And so she got to deal with Hexagon products across the full Hexagon life cycle. I wish that every young engineer got to have that kind of experience. She is now a solutions engineer in the system dynamics team, mostly working with Romax and products that directly connect to Romax to model rotating systems for customers or to support them in delivering their own simulation projects. Ginny, thank you so much for preparing and delivering this webinar. I really look forward to hearing what you have to share with us today.
Thanks, Alex, and hello, everybody. As Alex said, I'm Ginny, and I'll be presenting to you today. I'm looking forward to showing you how you can use Romax for design and optimization of your drivetrains. So today I'll be going through a few different models. First, I'll start with a quick introduction to Romax, and then I'll walk you through making a multi-speed transmission in Romax Concept. This will give you an idea of how to quickly design a model and make adjustments based on your requirements. So then I'll do a live demonstration of Romax DT. This will be a continuation of a model that was made in the webinar last year. So it'll be more of an in-depth look at analysis and optimization of that model. Finally, we'll let you know how to access the Romax software tutorials and the community. And at the end, there'll be a Q&A session, so you can ask your question. So Romax started as a specialist consultancy in gearbox, bearing and drivetrain systems. Over time, it grew into a leading software provider, supporting the design and validation of electric drivetrains and enabling early NVH prediction. So Romax has helped OEMs and suppliers create quieter, more efficient and more durable products. It's headquartered in Nottingham, but it has offices all across the world and supports customers across automotive, aerospace, wind, marine, rail and bearing industries. Today, around 70% of cars globally are developed using Romax technology. So how will you be able to use Romax? Well, in the past, engineers often relied on hand calculations or general tools like Excel. These were later built into basic software for gear and bearing design, but they didn't account for system level effects like misalignment. So to address this, people turned to full finite element analysis. But while this was much more accurate, it often was very slow and complex. And it was very difficult to change the design and optimize things. So you could only use one version of the design with little room to explore options or account for things like manufacturing tolerances. Romax was developed to overcome both of these limitations in approach. It provides a near full 3D simulation accuracy, but remains fast, repeatable, and easy to use. It allows for efficient design space exploration, CAE-led design, and consideration of manufacturing variations and tolerances. It offers 6 products, but I'll just focus on the first 3 as they're likely to be most relevant to you. So the top left there is Concept. It's used early in the design process to quickly explore layout options and understand how design choices affect system performance. There's also Romax Enduro, which focuses on detailed durability and efficiency analysis of bearings, shafts, and gears in the full system. And then the Spectrum helps identify and solve NVH issues early, so before they become expensive problems later on. Together, these tools support faster, more informed design choices and help reduce costly changes down the line. And first, I'll be showing you Concept, and then then be giving you a demonstration of Romax DT, which is a combination of the 6 products, basically. So in terms of your design and optimization of drivetrains, you'll be able to vary the gear ratios, their layout, the component sizing and housing, the bearing and gear design. And then you'll be able to see the effect on efficiency, performance, mass, durability, and many other things. So the first thing I'm going to do is start with a demonstration of Romax Concept. It won't be a step-by-step tutorial, but it will give you an overview of what you can do with Concept. It's probably the simplest Romax product to use, and it can very quickly build up models, so you can play with the layout and the sizing. I'll be using it to make bearing selections and also choose gear ratios in a multi-speed ICE. If you want to take a look at the tutorials for Concept, I've put links in at the end of the presentation. So this is Concept, creating a new model. Just this. When we start out, we're going to see the 2D worksheet, and it is a 3D model, so you can see the end view on the right-hand side there. But I'm just going to start by adding some shafts. So clicking this shaft icon here, and placing some shafts into the model. And then you can move them about using the pane on the right-hand side. So just by clicking on the mouse, you'll be able to move them around like this. If you want to do a more detailed look at dimensions and things, you can turn on that checked box on the left-hand side, and that turns on the current component dimensions. So we can just change the length of these shafts. One is 300 and the other one is 350. You can also change the width and the bore of the shafts as well. So these have mass and inertia already associated with them. And we can go on to add some gears. There's a few different gear options in Concept. There's bevel gears, worm gears, but I'm going to add some spur gears to start with to build up this multi-speed ICE. So you just click the icon and then you can click on the shafts to place them. These gears are the most basic design of gears in Romax, so they're called loading gears, and they're basically just represented by flat discs. I'll show you in 3D later. Yeah, I'll just add an extra there, so I'll delete that, and then we can mesh the gear pairs just by clicking on that meshing icon and selecting them one by one. They automatically go to a 1-to-1 ratio, and this ratio is just defined by the circumference of the gears. So for these loading gears, that's the only sort of changeable thing we can do with them at the moment. We can change these ratios either by sliding the gears on the worksheet, or you can just type in the ratios that you want. So I'm going to put in just some gear ratios here. And then what we're going to want to do next is, it's gone a bit slow because of the streaming, but I'm going to change the mounting of the gears. So at the moment, they're rigidly connected to the shaft. But if I just double click on each of the shaft connections, this will represent like a synchronizer or a clutch on the output shaft there. The next thing to do is to add mounts so things don't go flying off into space. I'm going to add some concept stiffness bearings. So these, again, are very simple bearings, which can later be upgraded to detailed bearings. I'll show you how to do that later. By clicking on that yellow icon that comes up in the corner, that just means all of them are grounded now. So all the shafts are completely constrained, and I can just add the power loads. So that's the input power and the output power are added. But we don't have any load cases at the moment. So if I click down here, you can see that load case at the bottom is just empty. So clicking this arrow icon creates a new load case. Now we're on load case 1. And just clicking through each power flow to create a new load case there. So I'll go through the first gear and then each one for the 5 different load cases for each different power flow. And you can see every time I click that arrow button in the corner, it just automatically creates a new load case, which will have a duration and a speed and a torque associated with it automatically, but we can change them later. That's third power flow, and then fourth, and that's the final one. So we should be able to see all of the load cases in the load case grid now, and we can make adjustments to any of the durations or speeds or torques at this point, and Romax will automatically fill in the empty boxes. So you can see in yellow there, it's calculated those values rather than inputted them. And that's our model fully made. So if I show you the 3D model, you can see what I was saying about the simple gears here. They're just modeled as flat discs. And I'll show you later how you can upgrade them into more detailed gears, because that will help with rating the gears and more detailed ratings of them. I've just gone into the reporting tab here, and you can see lots of different things. Not everything is available at the moment because we haven't gone through every single detail of the gearbox, but we can see a load case summary. So this shows us everything we've inputted with the load cases. This is quite interesting as well. So we've got the velocity and engine speed graph here, which is affected by the gear sizes. So we can see how they're affected later when I go back and change them. If we want to get some different speeds or a smoother profile diagram there. Looking at the gears, it's also quite useful to see the safety factor of the gears. So all of these are looking pretty good. If they were a bad safety factor, they'd be highlighted in red. So all of these are looking quite good. But again, we can go back and change the sizes of the gears, and that will affect that. In here, we're going to look at the bearing load ratings. So to do this, we've got to run the analysis again, but it will show us the ratings for each of the concept bearings. And that will help us make a decision on what kind of detailed bearings we want to add to the model. The first thing I'm going to do is just change that gear ratio, see if we can get some different speeds in that saw profile diagram. I change that to 1.8 instead of 1.5. And then I'm going to upgrade one of the stiffness bearings to a detailed bearing. So if I say select bearing down here and apply those changes, rerun the analysis, and we're going to get the bearing catalogue. So in Romax, there's all these bearings in this catalogue that you'll see when you open it up, and you can just put in your different dimensions and it should find you a gear that suits them. I'm going to put in a diameter and a width that I want. Also on the right hand side, you can select which kind of bearing it is. So I've selected a ball bearing, but you can put in a tapered bearing, or see what else, a needle bearing, whatever you want. I put in a higher dynamic load rating as well to make sure that it will have a long lifetime. Let's choose the one I want. And at this point, you can also choose how it's mounted. So the inner mounting, I'm going to leave as fixed, but you can choose it to be sliding as well. Now that the model's been updated, the report will just immediately update as well. So we've got a new saw profile diagram, and we've also now able to see the bearing ratings. So there's only one bearing that has been upgraded in this model. And that's the only one that's going to show up in these life ratings. But because it had a good load capacity, it should, yeah, it's got a very high life, 8 to the power of 5, you can see there, and only very, very small damage. So that's a quick look at how to create a model in Concept. One thing I just want to show you as well, I was talking about with these gears. So if I double click here, we'll be able to see that it's a loading gear. Like I said, this is just based on the size of the gear. And it's just sort of a disc shape in this 3D view here. But if you upgrade it to a concept design, that allows you to input the tooth number or the modular ratio, depending on how you want to define these gears. So that's a bit more detailed. And then the highest level of detail of the gears is this detailed design. And you can see that's the most complex gear that Romax will do. You can put in the root diameter, tip radius, all sorts of things, and then the gear ratings then will be a lot more accurate. So that is a quick look at concepts. I'll be going through an example of an EV gearbox next. So this was, like I said, modelled in last year's video. And I provided a link to that at the end of the presentation if you want to see how that was made. But it's a compound planetary model, and I'll walk you through the different components of it. And then I'll show you how to optimize it. I'll also show you at the end how to generate a duty cycle. Oh, sorry. So I'll go into Romax. This is our model. Show you the inside of it. Okay. So inside here, what we have is a electric machine assembly in this assembly tree here, and that's mounted on a rotor shaft. Yeah, and you can see this electric machine is within that assembly. It's also got bearings mounted on that rotor shaft. There's 2 planetary assemblies here and here, and both of these contain planetary gears, and they've got 3 planet gears, one of which is, well, 2 of which are copies of the first. So if we make any changes to this first gear, they will also be copied onto the second 2 planetary gears. And then we've also got a sun gear in the middle of this planetary gear set. The first thing I want to do is show you how to change units. So at the moment, I've got it set to SI units. So if we go into this preferences, and then that will show us the global preferences, scroll down and we can see the units manager here. And you can change your units within this. So if I click English, that's going to give us imperial units. If I click metric, that will give us SI units. If you want to change individual things, you can just change them here and click whatever you want. But I'm not going to change my units. I'm also going to add a lubricant to my model. So at the moment, it doesn't have a lubricant, and that will mean that some of the ratings won't be able to run, or they'll be a bit less accurate. So by adding a lubricant, it will allow the analysis to run. Okay, so I'm going to add this lubricant. It's okay. And nothing changes on this screen, but if we click this little lubricant icon here, you can just make sure that that has been added to the model. So you can see the lubricant level is about halfway for this one, and that's good. So now that we've gone through the gearbox, I'm going to run the analysis and talk you through the results. So the load case that I've got now is just a simple load case. We can see it in the load case grid here. And I'm going to run it. It shouldn't take too long. So we're going to get a lot of warnings and information in this box, but there's no errors, so that's fine. I can close that. And now if I go across to the reports tab at the top, we can see all the different reports that we've got. So we've got deflections, and that will show us how the gearbox is moving. It doesn't show the FE housing deflections initially. So you can see it's just the shafts at this point. I take away the housing, and you can see how that's deflecting in the greatest areas of deflection there. But if I do want to see the housing, I just click on this calculator here and add the housing components that I need to. That will take a while, so I'm not going to do that. Also, you can see the bearing results at the top here. I'll just go through a couple of things. So if I click on this first bearing, you can see the static safety factor is very, very high. And also, by update report, the life is extremely high. That's because it's not experiencing a lot of load at the moment. But if I go to one of the planetary bearings, it has a slightly lower static safety factor, and show you the life of that one is a lot lower as well. So you can use this to make some changes to the bearings. You can swap it out for a different bearing. You could change the clearance on the bearing, that might have an effect on life, or the lubricant as well, which you can set specifically for different components if you want to. What I'm going to show you is the gear contact patch report. So I'm going to pick the first planetary gear set, the Sun to the Planet Gear 1 gear mesh for the first load case, and generate that report. You can see that it's not the best contact patch. It's got a lot of loading on the right-hand side, and it's going to have quite a bad TE for this contact patch. So what I want to do is optimize this gear set. And there's a couple of ways you can optimize things. You could go into the main gearbox assembly and go to analysis and run a parametric study. But because I just want to do it for these planetary gears, I'm going to right click on the planetary gear set and select parametric study. So this will come up with the parametric study window, and we can choose a couple of different study types. So you could do the optimization with Romax genetic algorithm, sensitivity analysis. I'm going to go with this design study full factorial. What it recommends is to do 9 steps, and I would recommend you to do that as well. But I'm going to lower it to 6 just to make it a bit quicker than I'm showing you guys. I'll make this slightly bigger. So what I want to optimize is the microgeometry of the gears. Actually, I'm going to show you how to find the microgeometry first. So if I click on the gear set, it's going to take me to this page with the details of the gears. And go along to modeling. You can click microgeometry to find the microgeometry. At the moment, they don't have any microgeometry applied to them. So you can see on each rank, there's no microgeometry here. This is for the Sun gear and also the Planet gear. It doesn't show you the second and third Planet gears because they're just copies of the first one. So we can change this first Planet gear and then the other two will change as well. But if we want to add microgeometry, we can click in here and add some lead crown, lead slope, or involute barreling and slope as well. But because I don't know what microgeometry to add, I will do this optimization study. So if I go back into that, right click, parametric study, and it takes me back to my parametric study. I need to know what kind of microgeometry to add on the right flank of the planet gear, because that's the driving flank of the gear. So if I go into the right flank, I can see all the different things I can change. I'm going to select involute barreling and lead crown for now. Let's do a triple click on that. There we go. First thing I'll do is I'll change the name of this, because it's a bit long down here. So I'll call this lead crown. And I want to vary this from 0 to about 10 microns, because it's quite a small gear. So for this variable, it'll be going from 0 to 10 microns in 6 steps and seeing how that affects the outcome. I also want to change involute barreling and put that one, and also vary that from 0 to 10 microns. So there are my two variables. You can add more, but that will add a lot more time to the simulation. So I'm not going to add any more variables there. You can also add in variable constraints, which I don't have. So I'm going to move on to actions. So what I want to do is look at the effect on the sun gear to planet gear. I'll click in there, or this duty cycle and this load case that I'm looking at. And within the microgeometry, I can run microgeometry analysis. That's what I want to do. So I'll double click that. And my targets will be the things that I want to optimize. So I want to optimize TE, just to keep the noise low, and also KH beta, which should hopefully make a much nicer looking contact patch for our gear set. So within, again, these two, this gear mesh here, the center planet gear 1, I go into the duty cycle, into the load case, open up microgeometry, and here are all my targets. I want to reduce KH beta. Again, I'll give it a name. Beta. And I want to minimize that as close to 1 as possible. I also want to minimize TE. Ooh. And that one. And I'll call that TE and minimize that. So now the optimization study is all set up. I can just click run, and that will run the design study for me. So it shouldn't take too long because there's only 36 candidates. As you can see, each candidate is getting a nominal score based on the TE and the KH beta that it's producing. You can also change, even as it's running, you can change the X and the Y axis. So I'm going to put it on involute barreling and lead crown. So we can see all the different candidates being run. So that is completely run now. And if I turn on the Z axis, that will show us the TE. And I'll turn it off scatter so that we can see that more clearly. We'll do this from the top. We can then see the most ideal lead crown and involute barreling for getting the best TE. But I can also change the Z axis to KH beta, and that'll give us different results. So what we want to look at is the nominal score, which is a combination of both of them. Go back from the top. If you want to see precisely which candidate was best, you can go up to the report tab at the top there, and it will tell you the top candidate here. So that's saying that it got a nominal score of 0.905, just the lowest score. And that was with a lead crown of 0 microns and an involute barreling of 6 microns. So I'm just going to go back to the presentation and show you when I ran it with 3 variables and 9 steps, which took slightly longer, I got this outcome. So it told me for the sun gear, the ideal barreling was 5 microns, the lead crown was 1.25, and the lead slope was 0. I did the same thing for the planet gear, and I got these results. So I'm now going to input those results back into my gear microgeometry in Romax. Now that I've got that optimization study done, you can either go in here and add in your microgeometry, or you can use the spreadsheet, which is a lot quicker. So here, this is just telling me that Planetary Gear 2 is going to be a copy of Planet Gear 1, same for Planet Gear 3. And this is the spreadsheet for all of the microgeometry. So I know that I want the sun gear, a lead crown of 1.25 and an involute barreling of 5 microns. For the planet gear, I wanted 1.25 lead crown and involute barreling of 6.25. So as you can see, hopefully, this automatically updates for the other 2 gears. That's already in there. The planet gears. I press OK, and that should update the microgeometry, which you can see down here in this 3D view. So now that I've got that microgeometry in, I'm going to run the microgeometry analysis for this load case. And hopefully we'll have a much improved contact patch and also an improved T for the gearbox. If I show you, this is the contact stress for this gear pair. And I'll go back into the reports, take a look at the contact patch. There's these 2 gears. And you can see the load per unit length is also much improved there. I'll just show you a side-by-side comparison of the before and after, so you can see. So you can see the T is much improved, the KH meter is much improved, and you can do this optimization for any component of the gearbox. Like I said before, if you go into the main gearbox assembly and into analysis, once it's loaded, into analysis, you can do a parametric study, and instead of just being for that gear set, you can do it for anything in the entire gearbox. So the last thing I want to show you, after you've optimized your gearbox, you might want to run lots of different load cases. So I will show you how to add in, if you've got time history data that you want to use, I'll show you how to add that in to Romax. As I showed you before, we've just got one load case here, but we can see all of our duty cycles if you go into this DC editor. So we've only got one duty cycle at the moment. And what I want to do is add in my own data. So I'll go to generate load cases from recorded data and add generic and multiple path load methods. Yeah, that's fine. And then in this available time histories, I've not got anything at the moment. So I'll add in my own data. So this is a CSV file. I'll show you what it looks like in a second. This is my time history data that I'm importing. So if I click edit, you'll be able to see it down here. but Romax can't read it yet. So I need to tell it that the delimiter is a comma, and now Romax can read it. So it will just take a second to load. And then I can put in my quantities at the top. So to just briefly explain what Romax is going to do with this data, it's basically taking the data and turning it into a histogram. So each histogram bin is going to have its own torque, speed, and duration. And it will just work this out using the data you give it. So I'm going to tell it that this is time. This is the power flow that I'm using. This one is torque, and this is the speed. And now that automatically puts in the units, but I'm just going to change these to seconds. So I want to get rid of these top two lines by telling it that there's 2 lines of header. And that will update. And that data should now be able to be brought into Romax. So if I click OK, I can now add that into my time history. And if I want to scale up this data for a certain amount of time, say 200 hours, I can do that. And now I'm going to tell it how to calculate those torques. So I'm going to tell it to use the upper limits of the histogram bins to calculate the torque for each load case. So if I press OK here, that's going to generate all my different load cases. And now that I've got them, what you can do with that is you can either run each load case one at a time and see what your results are. You can also run a whole duty cycle at once using this static analysis button here in the duty cycle editor. And you can also edit each load case based on, so for example, you can change the temperature for each component within the gearbox and change that according to each load case. They should all be in here, and you'll be able to change them all individually. You can also edit different attributes within the gearbox. So, for example, if I show rotations within the gearbox, you'll be able to do this according to each different load case as well. Yeah, that's a brief overview of Romax DT as well. And I'll just show you how you can access the Romax software. So this is where you can find the Romax Community and the concept tutorials. And then there's also more links here where you can get the software and find the webinars. So I think I'll hand back to Alex now.
Thanks, Jenny. That was really helpful. I work in academic programs for Hexagon, and I want to step back and help you get a bigger picture view of what we can offer you, especially if you're on a student team, but even if not. So to access our software, if you are a student team, you can apply for the student competition bundle, and that would give you access to a variety of software listed here, including Romax. Oh, Romax is not on that list, but it should be. That was an error. We also have free Hexagon student editions. Those are free for students and professors all over the world. And to sign up for that, we've got, a little bit of a different process. Those are not, unfortunately, the full commercial versions of the software. They are normally limited in model size, and we do not currently have a Romax student edition, unfortunately. We have a number of webinars coming up. Most of them will be on Wednesdays, but some are on Tuesdays, including the one next week. We'll be dealing with a varied range of Hexagon simulation software with a major focus on vehicle dynamics with Adam's car, but not just that, also talking about finite element and CFD, and actually for finite element, going deep on composites and generative design. The webinars are available on YouTube. We have a link for that. You can follow us on LinkedIn. We would encourage you to join that page where we specifically post information that's helpful for people in academia. Oh, not listed on this slide, but very helpful is the webinar homepage. And if you're watching on YouTube, that's in the description. And if you're here live, it's in the chat. And that will give you access to upcoming registration links, but also Ginny's model files that you can use to compare your results if you want to work through the tutorial yourself, and the slides that she shared. So we have a lot of resources for you to help you out. And if you want to reach out to me specifically for help with accessing our software, feel free to do so. If you're watching on YouTube, we have contact information listed in the description. All right, with that, Ginny, I think that we're ready for questions. Let me start off with really big picture. Concept seems to be easier to learn, but has fewer features than drivetrain. How would a team know where to start? Would they want to start learning concept or drivetrain? Do you need to know concept before you learn drivetrain? If you jump into learning one and you work out that you really need the other one, how much of a waste of time is that?
I would say that drivetrain is a slightly more complex version of concept. So I started learning just with drivetrain. I didn't start using concept until quite recently, actually. So it is easy enough just to use Romax DT as when you start, and you can use it on a simple level. So using that 2D worksheet as well within Romax DT. But I would say if you're choosing to start with one of them, I would go with concepts because there's less buttons to get used to, there's less things to set up initially. So you can definitely dive in a lot quicker using concepts. And then it's very easy just to upgrade your model to Romax drivetrain as well.
That's great to hear. Do you have a recommendation for at what point in a student competition vehicle design cycle, when is Romax the most valuable? Like, do you already need to have your engine or motor chosen, or do you want to use it right at the start of the design?
You could use it at any point during the design. So as I showed you, you can input pre-made bearings and you can input electric machines that you already have and just put them into the software to test how to optimize other parts of your drivetrain. But if you want to just look at specific components and see which one to pick initially, you can also start at that point. So you can definitely start with a very basic model where you don't know many of the variables and build it up from there.
That's great. So I'm not seeing a lot of questions from participants in the Q&A. I'm going to give you another minute or so to enter something. And if you want to ask your question live, you can unmute and ask that question, or like you would request that in the Q&A, and then I could manually unmute you. Oh, I have another question for you. How would you see Romax productively connecting to other Hexagon simulation tools at different points in the design process? Like, would a team be able to import a model from Romax into Atoms, or would they want to link them together? Or is it that those two products are doing enough of a different thing that it's not worth forcing that connection?
I might have to pass over to Reese for this one. I believe you can use them sort of in sync, but yeah, Reese, you know a bit more about this, I think.
Yeah, so I think there's often a link as you go through the design process within Romax itself. So, you're starting with concept for your layout design, changing everything, and then you progress into the Romax DT environment where you can start to add more detail and go into even more depth of the analysis. But in terms of integration with other software, you can quite often use MSC Apex for meshing of complex finite element components and bring those directly into Romax to see how those components affect the system level deflections in your model. We also have a link with Atoms as well. So we can also take the Romax model, which is often we simulate in the sort of static environment. So we're just looking at static deflections around a given load case. But we can export that to Adam's view, I should say, to look at how the system might perform in a transient or time domain approach, and see, if you imagine you've got gear changes within your system, seeing how those changes in the operating conditions of your gearbox affect the load spikes in your system and how they could introduce damage. There is also as well, maybe not so important for Formula SAE or Formula Student, but maybe for other competitions where noise, vibration, and harshness might become more of a concern. We can also within Romax do some frequency-based dynamic analysis, so frequency domain, and we can get that information from Romax as well and link that with Actran, which is Hexagon's acoustic analysis engine, so that you can look at airborne noise within the system as well, and how that affects the quality of the transmission, the perceived quality of the transmission. So there are numerous links within Hexagon software that we can undertake with the software.
Yeah, and it seems to me that a lot of those connections really could be very valuable for a formula team. I know that getting people using different tools on the same team to coordinate, there can be some challenges there, but it can really be worth trying. For some of those connections, it seems like those are used a lot in industry. They might be overkill for formula, but it also seems to me that a lot of formula teams, people on them are interested in having successful careers. People doing simulation on the team want to be able to do simulation in industry. And I know that NVH, noise, vibration, and harshness analysis is just really important and only becoming more important in automotive. It's not a topic that a lot of undergraduates are necessarily exposed to, but if you can at least start to gain awareness of how that's being simulated, as a member of a student team, you might not be doing it on your vehicle, or you might want to try just to see what it's like. Being conversant in that at least can help you in job interviews and help you get oriented on what your long-term career track might be.
Exactly.
With that, Jenny, I want to thank you again for preparing such a clear and thoughtful, helpful presentation. And Reese, thank you for joining us also. I appreciate you supporting this effort. And I want to thank everybody who attended. I am glad that you're interested in checking out Romax. My full-time job is to help students and professors use our software. Feel free to reach out to me or to the university email address that will be in the YouTube description so that we can help you get on board with Hexagon simulation software for student competitions and really for any kind of academic use. That is what we are here for primarily. And if you're an industry customer who happens to have checked out the webinar, welcome. There are other ways that are good for you to get in touch with Hexagon. Okay, well, thanks everyone. I'll see you next week for the webinar on Cradle with CFD. Okay, bye.
Thank you, bye.